So today we'll talk about the rest of the motor system. So I talked about the superior colliculus, and particularly like the deep superior colliculus, the frontal eye fields. That was this whole complicated circuit that deals with eye movements and predicting what the world is going to look like right before you make your eye movement. And that takes up a good chunk of the motor system. So if you look in the striatum, for instance, about a third of it is involved with eye movements and orienting type movements or neck movements. But let's talk about the rest of the motor system that deals with the rest of the body, and just have an overview of what are the main parts of it. So that's the goal today. And then in the second part, I'll talk a little bit about hierarchical motor control and the idea of central pattern generators and how those things have evolved. So let's start with the sort of motor system overview, and I'm going to draw some sections over here, like where stuff comes out, and then there'll be some diagram of basic connections over here, and then I'll talk about the pattern generators over here. So let's start off with the most basic motor output structure, which you might not guess, and that is the reticular formation. So we'll put it down just about here, yeah. So reticular formation. So what is the reticular formation? So what does reticulum mean? It means net, like a fisherman's net. And so the reason they call it that is if you look in the reticular formation, which is kind of in the center, the bottom center of the neural tube in like the pons and the medulla and the midbrain, it's got a lot of very large neurons in it, and they kind of interlace like that, and so it looks a little bit like a net, and that's why it's called the reticular formation. And that projects down to the spinal cord, but not just the spinal cord. It also goes to motor nuclei in the brainstem that control things like the jaw. So you have to control the mouth and the jaw and the face and the neck and stuff like that. So it's not just the feet and the hands, but it's parts of the face also. So there's another branch that goes off to brainstem. So it's still in the brainstem. Say brainstem, motor, cranial. So there's in the spinal cord, stuff comes out of the bottom of the ventral part, the stomach part of the spinal cord, and it goes to muscles. If you go up into the brainstem, there's still wires, cranial nerves coming out, and they're related to the ones that come out of the spinal cord, but just higher up. And so those are called the cranial motor nuclei. So brainstem, motor, cranial nerve nuclei. So like say the trigeminal, the motor nucleus of the trigeminal that controls the jaw and other things like that. So the reticular formation goes to those as well. So where is the reticular formation? So if we look at sort of a picture over here, so you've got, so let me move it over a little bit so I can draw in between it. So if we look at the brainstem, remember there was like the alar plate, that was the sensory part, and then there was the basal plate. So it was sensory over here and motor over here, roughly. That's sense mote. So where is the reticular formation? It's pretty much, it's kind of like sitting right here. Now, sometimes people put like the median raphe nuclei. There's some nuclei that are right on the midline that are involved. They're particularly involved in like sort of sleep. They kind of paralyze you when you're, especially when you're dreaming. Like when your cortex wakes up when you're dreaming, it almost looks like it's awake. And if you let it do what it wants to do when it's awake, it'd move you all around. So the raphe turn on when you're dreaming and paralyze you, so that you can just dream without actually thrashing around. Although sometimes they don't work that well and you start thrashing around a little bit, but most of the time you get paralyzed when you're dreaming. So that's often considered to be part of the reticular formation. But here's the one that we're really talking about that have these, large cells in it. Looks like a net. So that's in the, that's in the pons and the medulla. And if you go back into the spinal cord, so if you go back down into the spinal cord kind of has a reticular formation too. So there's the ventricle, and here's the dorsal horn, and here's the other dorsal horn that is the sensory part of the spinal cord, and then there's the motor part of the spinal cord, the ventral horn. So if you look at, I scrunched it down a little bit too much. So if you look at, remember way back when, it sort of seems like about 7 months ago, we talked about the layers in the spinal cord. There were all these kind of, layers in the spinal cord, and then there was one layer, and not really a layer, it's kind of like more like a whole area right here. And that one was called Rexed, because that was this Scandinavian guy that did this Rexed lamina, which just means layer 7. So the 7th layer of the spinal cord is basically the reticular formation of the spinal cord. That's the original reticular formation. It's kind of in the same place. It's on the bottom and sort of kind of in the middle. And it's kind of like, it's really a sort of a coordination center for controlling multiple muscles. So you can think of this as, the reticular formation of spinal cord. It's kind of higher level spinal cord. So that's, and it's in this, if you just trace it up anatomically, if you cut sections and just come up from the spinal cord into the midbrain, you'll see that this region right here is pretty much in the same place as that. It's continuous with that region in the spinal cord. And so if we look at how the connections work here, well, the connections basically come out of the reticular formation, like here, and they generally go down to the same side of the brain because there's the midline, rule of Serino. So the pons and medulla are behind the pons midbrain junction, and so they project. So the right reticular formation mainly controls the right body. But the reticular formation extends up into the midbrain also. So if we sort of draw like a rough picture of the midbrain, here's the superior colliculus over the top, something like that. There's the ventricle, so that's the superior colliculus. And we look at the structures in the midbrain. One thing that's in there is called the red nucleus. That's not the reticular formation, but if we go sort of above the red nucleus in this region right here, which is kind of in the same place as this region over here. We have to do that in red. So that's the red nucleus, and then this part here in the middle. So let's label that. So this guy is the red nucleus. We'll talk about that one in a second. That's another major motor output pathway. It's very slightly red, not very red at all. Let's move it down here. Red nucleus. And then this thing here is the midbrain reticular formation. And there's a structure in it you don't have to remember this. There's a structure in it called the cuneiform nucleus, the wedge-shaped nucleus. Now, that's the problem with these names. Like, how does that relate to the cuneate? So the cuneate, remember, this is on the test, the cuneate is the part of the brain that receives input from the dorsal column nuclei. Remember that guy? It controls the hand, goes up to the ventral basal. So that's another wedge-shaped nucleus. So that one is wedge-shaped also. There's another one, there's a bunch of things in the reticular formation, but one of them is called the cuneiform. It's just a slightly different word, so cuneiform nucleus. And that's particularly involved in locomotion, like walking. So you can, if you stimulate the cuneiform nucleus, you actually get walking, coordinated walking behavior. So we've got the midbrain reticular formation there. There's the red nucleus. Cuneiform nucleus is one of the pieces of the midbrain reticular formation. But let's look at the connections. Now that one's in the midbrain. And so if you look at both the red nucleus, but also the midbrain reticular formation, it's going to have to cross in order to go down to the spinal cord, because it's on it's past the pons midbrain junction. So here's the pons midbrain junction. Here's the pons midbrain junction right here. The dotted line is the midline. So that makes sense. There's some projections that aren't crossed, but 90% of them are crossed. And so that's the reticular formation. And so if let's just notate all the main parts here. So we got, let's go a little bit over here. 4 main motor output pathways. And so number 1 is the reticular formation. So number 1 is retic. Sometimes they call that the reticulospinal because it's going down to it's reticular formation down to the spinal cord. So how about just call it reticulospinal. So that's a major motor output pathway. Now, the second major one we've already encountered, which is the vestibular nuclei. And I put this in quotes because, like I said, they get vestibular input, which is, important. You get vestibular input, but they're much more general than the stuff going on in there is much more general. Much more general than just vestibular input, because they get visual input, they connect up to the cerebellum, they get auditory input, a little bit of somatosensory, and they get a whole bunch of different sensory inputs, and they kind of coordinate. This is what I always say, they coordinate like your body is a 150-pound piece of chicken, and it's kind of delicate, like if it falls on the ground, it gets scratched up. And imagine imagine propping 150 pounds of chicken up vertically, and it constantly stays up. And I already gave this example, but if if I do something like just raise my arm up, if I didn't do anything, that would cause me to tilt. And so what happens if I raise my arm up? You can if you watch my head, you can see that my head slightly moves to the left. I don't feel like I'm doing it. I just, it just does it. And why is it doing that? Well, it's just slightly, the muscles are all contracting all over my body and just slightly tweaking my body to the left so that when I've got this heavy thing hanging out, which weighs like probably 5 or 10 pounds off to the side, it actually will balance things and keep it balanced. And so it's just constantly doing that. I could do the other one, goes the other way. You can't feel it. It's just constantly doing that to keep your 150-pound chicken from falling down and getting scratched up. So, so the reticular formation and the vestibular nuclei are the ones that are actually doing this. And so there's a big output that comes out of the vestibular nuclei, goes down to the spinal cord, and then it also goes to some of those, brainstem nuclei. Now, if we put those two together, so the reticulospinal and the vestibulospinal, they have sort of a function, sort of a common function. And what that function, so if you read in a sort of a neurophysiology textbook, they'll say that these control extensors. So what does that mean? Controlling extensors. It's kind of a something that means something that extends your limbs away from your body. So like when I do something like this, I extend my limbs away from my body. Now, what about a leg? So like if a leg is up, it's not extended. If a leg goes down, then it's extended. So these guys control extensors, but that's not really the appropriate. Let's put it on this side. Extensors. It's not. It's more general than that. Really, what it is they're controlling anti-gravity muscles. Anti-gravity. That's actually the real functional distinction. And how can we tell that it's not just extensors? So if you look at an animal, like a cat, like a quadrupedal animal that uses all four legs on the ground, these systems essentially make the legs extend as opposed to sort of bring them in. So you would have, you would call these flexors because they sort of bring the limbs in. Those are extensors, they bring the limbs out. And so on a cat, the anti-gravity muscles are basically extensors. But what about a monkey, especially a monkey that's hanging a lot? So if a monkey is hanging from, especially in arboreal, some monkeys sort of walk around like baboons, like a cat on all fours, but other monkeys like a gibbon that are very arboreal, they support themselves by bringing their limbs in. And so if you look at these systems in something like a gibbon, they're actually controlling they're causing flexion because that's anti-gravity. And you can actually see a residue of this in human brain damage. So what happens, so we haven't talked about the cortex yet, but the cortex and the red nucleus are another two. Let's just write them in here. So we have the red nucleus. So that's the rubro spinal. Coming from the red nucleus. And then we have cortical spinal. And these are going to be sort of functionally distinct. These generally are doing flexors, meaning like bring the limbs sort of in toward the body instead of pushing them away from the body. But really what they are active movement. Is kind of like a better way of thinking what they're doing. So like in the case of a cat, when a cat is walking around, when it's pushing off the ground, it's doing anti-gravity. But when it lifts its paw up to make its next step, that's an active movement. So you can see these systems cycling back and forth very rapidly. Like when an animal is walking, it'll be like, red nucleus to sort of push off. It will be like, reticulospinal and vestibulospinal to sort of push off. And then when the animal lifts its leg, that will be red nucleus lifting the leg. So, certainly if a cat is sort of batting something around, that's these active movement kind of motor system going on. But to get back to the sort of why humans have a residue of the anti-gravity from an arboreal animal. So if you seriously damage the cortex, like remove the entire cortex, which can happen, you get in a car accident, you can take your whole cortex off. You'll get what's called a decorticate posture. And I always advertise this like this, good things to know at parties. Like, how can you recognize, I know that guy is decorticate. How can you recognize the decorticate posture? Well, no, if you do that to a cat, if you remove all the cortex from a cat, the cat will, all its extensors will be sort of like over activated because these systems kind of interact with each other. And when you take these away, these guys become too active. And so the decorticate posture in a cat is everything extended, all the front and back limbs extended. What about a human? You can recognize a decorticate human because they have their arms brought in, but their legs are sticking out. So their legs will be extended against gravity, but their arms are brought in. And that just reflects, our arboreal heritage, where we used to do this for anti-gravity because we were sort of hanging from trees not that long ago. So you can actually still see that. It's interesting. So this is kind of a higher level functional characterization of these two systems. So let's go back to the vestibular nuclei. And so where are the vestibular nuclei? So if we look at them from the top, so these are kind of looking at the brainstem. The neural tube is kind of extending in and out of the board here. But what if we looked at it from the top? Looked at the vestibular nuclei from the top. First, where are they here? Well, they're sensory nuclei. So the vestibular nuclei are basically going to be pretty much more or less where you'd expect to find the cochlear nuclei, except behind them. So this guy, vestibular nuclei, are right here. And the reticular formation is, right here, and also in the midbrain. So if we look at them from the top, so this is kind of like an end-on view, sometimes called a transverse view. But if we look at them from the top, there's a bunch of vestibular nuclei. There's 4 of them, and there's one with really big cells here, and then another one with kind of small cells, and another one that goes down here, another one that goes down here. And so these are I can never remember. This one's called the inferior. This one's called the lateral vestibular. You don't have to remember these. This one is the medial. So there's four distinct subparts of it that get vestibular input, and then this one is the superior. And there's been studies of what the subtle distinctions in what these different guys do, and it turns out just the lateral one with the giant neurons. The reason it has giant neurons in it is because it's going down to the spinal cord. So just these guys and this inferior actually go out. So the other vestibular nuclei they're more sensory nuclei that go into the system, but these two are the main ones that form the vestibulospinal pathway. So this is, to label this top view, vestib. That's the vestibular nuclei. So they're doing anti-gravity, getting vestibular input, but also getting visual input and a whole bunch of other stuff. Okay, so now let's go up to the original motor cortex. So the original motor cortex was the red nucleus. Just making some room for my wires. Okay. So was the red nucleus. And so the red nucleus is in the midbrain. It's right here. So this guy is the red, sometimes just called RN, red nucleus. So that's the original motor cortex. So the red nucleus is, let's leave some space for the cerebellum, so I put the red nucleus here. Red nucleus. And so this guy, so the superior colliculus is up here. I'll just put it in parentheses because we're leaving it out of the diagram, but that's that giant diagram of all the connections. We'll leave that guy out. But just know that it's there. We won't draw any connections to it. So the red nucleus comes out, and it goes down to the spinal cord, and it goes down to these guys also. So that red nucleus is you can sort of think of this as, the original motor cortex. So it has a map of all the muscles in the entire body. It can move the entire body. And that was kind of like the original, motor nucleus. And the red nucleus gets all different kinds of input. I won't draw, all its input, but it gets, a lot of different inputs. So we're just talking about the last output stage for the most part here. So that's the red nucleus. Now, why did I say it was the original motor cortex? Well, if you go back and look at something like a turtle doesn't have a motor cortex. So you wonder, how does a turtle move? Well, it moves with its red nucleus and its vestibular nuclei and its reticular formation. It can move perfectly well. Turtle has a cortex. There's a cortex in a turtle, but it doesn't sully itself with low-level motor details. It only does philosophy. So the cortex in a turtle is kind of higher level. It's at a higher level. So what happened in mammals are particularly good at very fine movements if you compare them to reptiles or something like a frog. Frogs are very effective flycatchers, but they kind of look a little bit less sort of delicate than if you imagine a little rodent running around with all this hyped up motor activity. And so mammals have very high performance motor systems. So do birds. So you can see the origin of motor cortex already occurring in raptor birds, like an owl. You can see there's a little motor cortex just for the talons. It's a cortex that projects directly down to the spinal cord. So what's going on here? Well, what's going on here is that you're moving the cortex to a lower level. That's important to sort of keep in mind, just the overall picture. So if you look at something like a turtle, like I said, if the turtle's philosophizing in its cortex and it says, I'm not going to mess around with the fine details of leg movements, you guys down below, the servants down below should deal with that. What happens in mammals is the cortex develops a new pathway that goes down to the spinal cord. And so we call this one, every year I call this one new. And since I used to be a geologist, what does new mean? Well, that means sort of less than 100 million years old. So if we go back to, if you go back to a reptile, it doesn't have this, or a frog doesn't have this, but mammals have this. So that's a new pathway that wasn't there in something like a turtle that goes down to the spinal cord, having the effect of putting the cortex, the motor part of the cortex, at a lower level, having more direct control. And what's the idea there? Well, the idea is that you could essentially move some of your pattern generators up into the cortex so that there'll be other areas of the cortex that could coordinate things, and then these guys, motor cortex, would have very low level access to the spinal cord, whereas in something like a turtle, you just do philosophy and then you talk to the striatum and you somehow get out of the cortex and eventually get down there. So it's an important point. We've changed the hierarchical level of cortex by essentially lowering it to something that can control specific muscles. So that's a new pathway. Okay, so you can see there's two obvious holes here, and so these obvious holes are for the other two major side loops in the motor system. These are often called side loops, and they have certain things in common with them. And so one of them is the striatum, and the other one is the cerebellum. So here's the cerebellum. So there was one more hole because we have to have the thalamus in there. Because remember this. So what's the striatum? So the way I'm using it here, I'm thinking of, if we go way back in the Dark Ages when we talked about the neural tube, how it splits into a Y when you're in the forebrain. So this is the forebrain. And then we divided it up into 3 chunks. There was basically the top part, that was the pallium, and then the medial part that's down, that was the septum, and then this down outer part, that was the striatum. We called that the striatum. The thing with stripes in it. And so why do people call it? Why was it called the striatum? It's called the striatum because if you look at it, say you look at the caudate and the putamen. We'll talk about these later. And then those project down to the globus pallidus, GP. That's one structure that you have in the forebrain. It's part of the forebrain. It's above the thalamus. But if you look at this structure, you see this big bundle of fibers kind of punching through it. And that's called this thing's called the internal capsule. Internal capsule. And so the internal capsule is just wires coming from the cortex going down to the spinal cord. If you look at something like a rat, there isn't, in a primate or a human, you see there's a big bundle where these fibers all sort of gather together. And something like a rat, they just the fibers just break up into like 100 bundles or a couple hundred bundles and just penetrate through the striatum. So there isn't any distinction between the putamen and the caudate. But in a monkey, which is where the striatum name came from, it sort of looks stripy. That's stria is just like a little stripe, and so that's why it's called the striatum. But it comes originally from the ventral lateral part of the forebrain ventricle. So that's the striatum. Thalamum. No, it's thalamus. Okay. So how does the striatum and the cerebellum get into the system? So if we look at the cerebellum to start with, so the cerebellum, we'll see the cerebellum gets a bunch of sensory input like from the spinal cord. There's a huge sensory input to the cerebellum. And then the cerebellum can go to the red nucleus. So that's one of the main things that goes to the red nucleus. And so that's the only way that the cerebellum can get out and do stuff. It has to go to the red nucleus, or in a mammal it can go to the thalamus also, and then from the thalamus it can go up to the cortex, and then it can go out through that new pathway in a mammal. So that's the only way that the cerebellum sort of can get out. There's not much. There's a tiny little output that goes down to the spinal cord from the cerebellum, but it's not very big. Is there a question?
No, you said it can connect to the thalamus for mammals, or you said it is a pathway?
No, that is a pathway. It's even a pathway in turtles. Yeah, from the cerebellum going up to the thalamus. But the main point here is that it's not a major output pathway like reticulospinal, vestibulospinal, rubospinal, and corticospinal. It has to somehow get out through one of these, and it can get out through the red nucleus. It also has projections down to the vestibular nuclei. It can get out through those, and it has projections down to the reticular formation. It could get out through those. Now, an interesting thing about this is that the cerebellum, we'll put like the cerebellum cortex projects to the deep cerebellar nuclei. We'll have a whole lecture on the cerebellum so we can get into this. So it goes to these deep cerebellar nuclei, but what does it do? It actually inhibits them. And this is a characteristic of the striatum as well. So the output of the cerebellum is, there's like 3/4 of all the neurons in your brain are in the cerebellum. More than the cortex, like 3 times as many neurons as you have in the cortex are in the cerebellum. So the cerebellum is doing all its stuff, but its output is strictly inhibitory. And so in order to sort of release a movement, the cerebellum has to turn itself down, and then a movement will be allowed. So this is an inhibitory, it's a very characteristic thing. You don't see this. All these other pathways are excitatory. These are all plus. Down here, these guys excite. They excite the spinal cord. But the cerebellum inhibits. Its main output is an inhibitory output. And the same thing is true up in the striatum. So when you look at the projection so how does the striatum get out? The striatum can only get out by going to the thalamus and then going up to the cortex and then back out. And if we look at that connection to the thalamus, it's inhibitory. So it inhibits the thalamus. Now, where does the striatum? Yeah, question?
Can you just quickly recap which ones exactly are excitatory and all the ones that split out?
Yeah, so all the ones, essentially everything's excitatory except for this output coming out of the cerebellum and this output coming out of the striatum. Yeah. Yeah, see, because normally what happens whenever you have a large neuron in it, if you look in the cortex, the pyramidal neurons, they're excitatory, and they excite other cortical areas, or they go out and go down into the spinal cord, excite the spinal cord. But the inhibitory neurons in the cortex don't tend to come out of the cortex. They just sort of go to their neighbors nearby. And so this is and that's true in most structures. Like if you go into the geniculate, the neurons that come out of the geniculate, they excite the cortex. There's inhibitory neurons in the geniculate, but they're all just sort of local. They don't send an axon out of the geniculate. And so this is a very characteristic difference where the main output axons of the big cells, like the Purkinje cells in the cerebellum, are inhibitory. Same way with the globus pallidus. The globus pallidus goes to the thalamus long distance pathway, and it's inhibitory. So how does the striatum get its input? Well, I mentioned it before. The entire cortex goes to the striatum. The entire cortex goes to the striatum, so it gets lots of input. But in order to get out, it just has to go down to the thalamus and then back up to the cortex. There's several other output pathways, but this is a major one. Get up to the motor cortex, and then get out to the spinal cord. And there's one more. This is the last pathway. So there's one more. We should draw some, a lot of input coming into the reticular formation. It gets all different kinds of sensory input. The reticular formation, and the vestibular nuclei also get all different kinds of sensory. So here we'll just call these sensory inputs. So that could be visual inputs, somato, visual, auditory. So there's a ton of sensory input, going to the, to the cerebellum, to the vestibular nuclei, to the reticular formation. But let's go to the cerebellum and look at another new pathway. Again, new in the sense of newer than 100 million years old, and that would be this pathway that comes from the cortex down to the cerebellum. So there's a pathway that comes down from the cortex to the cerebellum, and that wasn't there originally. So the cerebellum is mainly dealing with the red nucleus, and so all the structure, it's interesting when you think about these things, all the structure of the cerebellum, the Purkinje cells, we'll talk about that, how the cerebellum is laid out, was developed before it had any cortical input. And so this is another new pathway that really only mammals have. So new in quotes. So this pathway coming from the cortex down to the cerebellum. And it's gotten so big, like if you take a brain section or look at, an MRI scan, you'll see this tiny little thing like this that I always draw. That's the sensory and the motor part of the pons. And then there's this giant thing, like about that big, sticking off the bottom. Kind of looks like beef, or it looks like sort of roast beef or something. It's got all these little things, and that thing is the pontine nuclei. And unfortunately, despite their name, they act like they're in the midbrain. It's called the pontine nuclei because they kind of billow back and sort of cover over the pons. But what are these things doing? They're basically, the cortex comes down, this new pathway comes down, and it goes and synapses on cells on the same side of the brain. And then these cells cross over and then hit the cerebellum. So that's how the input from the cortex here gets into the cerebellum. And so you can see how much it's expanded. So this is a really important pathway. It's hugely expanded in humans. If you look at the cerebellum is expanded more in humans than the cortex has. If you look at monkeys, if you go back to a monkey, you can see we have a bigger cerebellum. We have a bigger cortex, but our cerebellum is even bigger than our cortex is bigger. So this is a very important part of humanness, is the pontine nuclei and the cerebellum. Yeah. Yeah, it's so you can so if you look at a turtle cerebellum, it's just like a little flap. If you look at a human cerebellum, it's folded up into all these little folds, just in one axis. So it's about more than a yard long if you stretch the whole thing out. It's this huge thing that really sort of expanded a lot. Okay, so that's the overall picture of the motor system. So we've got these 4 major output pathways. They have this functional distinction between them. And then, these are more anti-gravity. These are more sort of active movement kind of things. But even to the extent of just walking, it's like when a cat is walking, it's like vestibular, reticular, and then red nucleus, corticospinal, and then vestibular, reticular. So those things just flip back and forth just for every single walking step. And definitely like prey batting, like red nucleus, not reticular formation. Okay, so for the last bit, let's talk about the corticospinal, and introduce this idea of central pattern generators. And so this idea was originally developed mainly from studying insects or studying arthropods like the lobster stomatogastric ganglion. And so the lobster, you think lobsters aren't too bright, but they've got, they got some stuff. They're really good at smelling stuff. And they have a very interesting stomach. And the stomatogastric ganglion is a little mini brain that controls the lobster stomach. And if you look at what goes on in the lobster stomach, the lobsters, so what are lobsters eating? Like I always say, all different kinds of crap, so they're like rustling around down on the bottom and picking up stuff, and that's pretty good. We'll eat some of that. And when they eat it, what happens is it goes down into their stomach, and then the stomach's got all these detectors in it, and it can do different things. So if it gets something that's really hard, the stomach has these little chitinous, hard little teeth in it. And so it will go into a chewing motion to chew something if they get a little hard bit of crap that they picked up. If it's soft, it will go into this other pulsatile motion. And it's the same muscles, but 2 different patterns of activity that can be generated. And so people have studied how this happens, and they looked at the higher level neurons that project to the neurons that are controlling the muscles in the stomach. And so that's where some of these ideas were originally developed. They also developed for something like walking behaviors in insects. So walking behaviors, you have like a cockroach walking along. It's got these coordinated movements that happen, and then you've got something from the top that says, run for your life. This big shoe coming down. So let's just look at this in the case of the evolution of hand movements. So we're obviously very good with our hands. We can do all different kinds of things, play piano, make little tools. But we're not the only ones that are good with our hands. But let's look at a cat. A cat is not as good with its hands. It's very good sort of batting stuff around, but it's not that good with its fingers. And why is that? Why can't a cat play the piano with individual claws? And if you think about it, there's a muscle for the index claw. And so the muscle for the index claw will cause the index claw to come out from the index finger of the cat, basically. But you never see a cat doing that, just sort of going like one claw coming out. If they're trying to punish the dog, they put all claws out and bat at the dog. So why is that? And the reason is because if we look at our cat here, but many other mammals, other mammals are like this. Not all other mammals. What happens is if we draw the midline here, and here's put it slightly over, and here's the spinal cord down here. So we draw a nice big spinal cord. So it's got the ventricle and the dorsal horn and the ventral horn, and then the lamina 7 of Rexed in the middle there. Okay, there we go. So if we look down at the very bottom, we find the actual motor neurons. So down here you've got the actual motor neurons that are going out and synapsing on the muscles. So here's another motor neuron. And if we look, it punches out of the spinal cord, synapses on, these are supposed to be muscles. So if we look at the connections coming down to them from the cortex, so here's motor cortex. They come down and the motor cortex is past the pons midbrain junction, so they cross over, and then they come down, and where do they synapse? They synapse on that lamina 7 of this part right here. So they synapse in this area, and that's basically where the pattern generators are. So you can sort of think of these guys as pattern generators. And so what might they do? They might, like in the case of a cat, they might coordinate all the muscles, like all the claws and the arm muscles, to do a little bat. Like if a cat's like sort of batting at something, it needs to move its arm muscle and maybe stick its claws out all at the same time and bat at something. And so those structures will coordinate and synapse on all these different muscles, like the different claws, for instance. And so what's the problem with that? Well, the problem with that, if you say like, a cat says, I really want to learn how to play piano, well, in that case, you're going to have to sort of like just put the index claw out for a really small cat piano. But what happens is, the cat motor cortex thinks, I should put my index claw out. And then it just sends the command down to this pattern generator, and the pattern generator says, well, we've got clawing the dog, and we have sort of batting the little piece of paper around, but we don't have index claw program, so I can't do that. And so even though they have individual motor neurons that can control each claw, the muscles for each claw, they can't actually make a movement like this, where you just move one finger. But if you look at other mammals, like primates, but not just primates. So it turns out there's always a tendency to sort of go back to this medieval idea about evolution, that we're sort of leading up to, first there's rocks, and then there's animals, and then there's humans, and then there's God. And humans are closest to God, and animals are not as close. And primates are close to humans, and so they must be better than cats, because cats are further away from humans. But what about raccoons? Raccoons can do this too. So raccoons in parallel evolved very fine control of their fingers. So if you look at a raccoon has no trouble doing something like that. It can move its little raccoon index finger. And what is a raccoon? It's basically a small bear. They're related to bears. So small, little, cute, bitey little bear. And so raccoons have very good motor control. And you can see the same change in their spinal cord, in the connections into the spinal cord. And what does that change? So we've got to draw one more spinal cord here quickly. The dorsal horn, and that's the sensory part, and then the ventral horn, that's the motor part. So if we look at our raccoon or primate spinal cord, what happens is the motor cortex goes to the same parts of that pattern generators, because, monkeys have to be able to contract all fingers together to grab onto a tree. So they need the same kind of pattern generators that a cat has that activate all the finger muscles at the same time in order to sort of grip onto a branch and lift off. So they still have these same connections here where these neurons go and coordinate, several different neurons. And they might also just go and go into the white matter of the spinal cord and go forward to another part of the spinal cord to coordinate, some other further away muscle, because you need like arm muscle and the fingers at the same time. So that's all still there. So the motor cortex goes down and it crosses over and it hits these pattern generators. But in addition, what happens is you get some direct connections. And so the direct connections come out of the motor cortex and they go down and they skip the pattern generators and they go straight to the motor neurons. So this is like a direct to motor neurons. This pathway here. And so what does that do? Well, it's sort of similar to what happened with the evolution of motor cortex in the first place, because if you look at a turtle, it's got a high-level motor cortex, philosophy-only cortex, and then it said we're going to lower ourselves down to controlling individual muscles, but initially it just said we'll lower ourselves down to controlling pattern generators. But what happened in primates and raccoons is they said we're going to lower ourselves even lower to controlling individual muscles, so that we can actually essentially have control of individual fingers, like in a raccoon or in a primate. And so, and we'll see something similar to this, similar in songbirds. So if you compare like a duck to a songbird, you can see a similar kind of thing happening. What they've done is they've gotten direct control of the vocalization apparatus that normally would have had to have gone through the pattern generators. And so that's the end of the line here. So you can see how we've made motor cortex even lower in primates. And what's the reason for that? Well, then we could have some higher level pattern generators that would have sort of access to piano playing and all stuff like that, as opposed to just letting the pattern generators down here. So these are, we call these guys, central, pattern generators. So they're still there. We don't get rid of them because we still need to do coordinated movements like that. And if you look at, this corresponds to with looking at lesions. So if you damage the motor cortex in a monkey, it can still move all around. It can climb up a tree, no problem. But what it can't do is it will no longer be able to make really movements where you distinguish two fingers doing two different things. Like, for instance, if you have it try to get a little seed out of a slot, and it requires it, in that case, the animal looks at it and they can see that if it had its normal motor cortex working, it would just grab its hand together and just reach down into the slot and pick it out. It can't do that. But it can use all the fingers at the same time to climb up a tree, no problem.
This is like the creature. Does it have the emotional intelligence that it has prior, like ability to grab it, and now it doesn't? And does the monkey get frustrated?
Or the monkey could get frustrated, but animals, if something bad happens to an animal, they just kind of suck it up. They don't complain as much. Like if they even like just look at a dog that's lost a limb. It's just like, we're ready to go. I only got one front leg, but not a problem. Let's go out walking. So they tend to be a little bit more can-do. Sometimes humans are sort of a little bit more complaining than animals. So generally animals just say like, well, that's what happened. Life sucks. Let's just go forward. Okay, so any questions about the where these things are, the basic diagram, a couple new pathways that we got in the last 100 million years, this basic distinction between sort of anti-gravity versus active movement, and then these two extra loops from the striatum and from the cerebellum that can only get out by going to the red nucleus or going to the motor cortex. That's the quick and dirty summary. Okay, any last final questions there? All good? Okay, I think we'll end the recording there, David.